In this session, we will take a dive into the very deep fundamentals of the origin of electromagnetic nature of our matter. The gentleman who described that first time was James Clerk Maxwell, and the resulting equations still today are called corresponding to his name. In this session, we will have a set of topics. So first of all, we will start with some prerequisites to understand the electromagnetic nature, and that is current and charge density, electromagnetic field, and the Lorentz force. Then we will take a look at the microscopic Maxwell equations, derived from individual charges moving and displaced, and then we will integrate those to the macroscopic Maxwell equations and the material equations, which then will ultimately give us the description of the electromagnetic nature of our matter. In the last part, we will then interpret the four Maxwell equations according to their individual physical meaning by applying them to corresponding experiments. Maxwell summarized his work in one sentence, and it is so important and so well formulated that we just reproduced it here. Let me read it to you. The agreement of the results seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. Now, the important ingredient in this sentence is the word substance. It is the origin and the relation of the electromagnetic nature with the resulting consequences for the behavior of this matter, and as we will see later, directly from these equations we also can derive wave equations describing the electromagnetic wave itself, and here you see already the direct link of electromagnetic oscillating waves, which we call light, and the corresponding origin, which relates the electromagnetic characteristics of matter. To start with some prerequisites, we should understand that a charge is given by a microscopic distribution of charge density ρ, and we integrate over all charges to get the total charge. That's simple. Similar thing holds for the current, so that is for moving charges, usually electrons, which is represented by the current density J. And of course, if we integrate over the current density J, we get the total current I. Now, in not continuous distributions, we also could look at individual charges and simply look at the contribution at a certain point and position of that charge. This is expressed by this delta function here. So we do have charge at a point xj, we integrate over all j's, and the same thing holds for the current density J. A second prerequisite that we need is the behavior of charges in a static manner or in a dynamic manner. So here the static part, imagine two charges separated by a certain distance, then we know they generate an electric field between them, and this field results in a force which is simply the product of the charge and the electric field. So in the dynamic case, imagine a moving charge now, usually we consider an electron, and this electron generates a magnetic field in a circular manner. So that is what you know from the right-hand thumb rule. If the current is in the direction of the thumb, the resulting magnetic induction is just circular around the direction of motion. And the resulting force is the cross product of the speed of the charge and the magnetic induction B. This is the magnetic part of the force. And the electric part of the force is simply the electric field. So the total force is the sum of the electric part and the magnetic part. In this slide, you see the Maxwell equations, the 4 Maxwell equations, and they connect magnetic magnitudes with electric field magnitudes, so induction and electric field, and they also represent what we just discussed, moving charges in terms of current densities or static distributed charges in matter represented by the charge density ρ. To get a better understanding of the details, let us take a look at the microscopic behavior and distribution of charge. Usually matter is neutral and it consists of atoms which are made from negative and positive charges, but you don't see any effect of the distribution of the charges. If you look at a relatively large distance, those atoms are neutral. This changes as soon as we apply an electric field. If we do so, we get a resulting polarization, a separation of these charges due to the force, the electric force that we just rehearsed. And if you look at what happens, you see that the polarization gets visible. Depending on the size of the field, the polarization increases and the charges separate. As a macroscopic effect, already you see that at the boundaries we will get a net value of positive charges at the one side of the electric field and a net value of negative charges at the other side of the electric field. So there will be a summing up of these microscopic effects to a macroscopic polarization. Now we don't only have bound charges, we also have free moving charges, and this is indicated very simple by allowing also free charges to move around besides the fact that we have the bound charges in a solid state. In this slide, we now make the step from the microscopic view of the atomic behavior to a macroscopic characteristic of matter under the presence of an electric field. Again, here you see the free charges represented by the density ρ, and here the bound particles with the sub p index indicating that a polarization is possible, as we discussed before. And here you see the relation of the magnitude of polarization, which is then connected to the charge density of the bound matter just by the derivative. With the current density, it's a similar process. We have an averaged current density made up from free charges moving, building a current density J, and then the bound matter contributions in terms of polarization and magnetization, where the individual contributions are seen here. The polarization and the magnetization are the densities of electric and magnetic dipoles, with the electric displacement d and the magnetic field strength h. We can introduce two magnitudes connecting now the polarization and the electric field, respectively the magnetization and the magnetic induction, to the magnetic field and the electrical displacements. And then if we introduce these magnitudes and we combine them with the formulas above, we get one of the Maxwell equations, the so-called Maxwell-Ampere equation, which is this expression here. And we also obtain the Gauss law, which then takes the form shown here, connecting the dielectric displacement with the charge density ρ. So up to now we described a rather complex world of equations, however, with a simple general understanding of describing the reaction of electromagnetic matter to the presence of electric fields. And as a consequence, we now look at the material equations, so the material side, and how this behavior can be described from the materials point of view on an integrative macroscopic level. On the left-hand side, you see the general equations, the material equations, where J is the current density, is a function of the electric field. Of course, the field drives the charges, and that results in the moving charges. The dielectric displacement is connected to the electric field and the polarization, which again, as we will see, is the result of the presence of the electric field. And the magnetic induction is related to the magnetization and the magnetic field in this simple formula. Now, if we look at a rather simple boundary condition set, where we look at local distributions, isotropic materials, and where we have the assumption of a linear dependence of the individual magnitudes, then we result in these equations here. The first one is that the current density is given by the electrical field, which drives the current, and the proportional factor, the factor of proportionality, is simply the conductivity sigma. This you know by Ohm's law. The second equation reduces simply to a proportionality of the electric field to the polarization. So here obviously the electrical field drives the separation of the charges, the bound charges, and the proportionality factor is simply the susceptibility. This is very straightforward because it tells you how susceptible a material is in its reaction to the presence of an electric field, resulting in a corresponding polarization. And the same thing holds for the presence of a magnetic field, where the proportionality factor, susceptibility sub m for magnetic, gives us the value for the magnetization. Again, now putting these equations back into the material equations, we get these simple relations as you may know them from simple physics courses, where you simply end up with the linear relation between the electrical displacement and the electrical field, and corresponding the linear combination and behavior between the magnetic induction and the magnetic field. Taking a closer look at this relation between the dielectrical displacement and the electrical field which is applied to the matter, we observe that the factor of proportionality is the permittivity of the material. Now this permittivity actually is the footprint of the material in terms of its behavior reacting on the presence of electric fields. So this permittivity represents material properties which will give us an understanding of how the matter reacts with this electric field which we apply. Will it be reflected, transmitted, absorbed? And for the simple assumption of an harmonically bound charge, we can plot the permittivity against the exciting frequency of the electromagnetic wave, and you already see a dispersion relation here for the real part representing later on the index of refraction, and an imaginary part which will give us an answer to the absorption characteristics of the material. So that is already in these equations here. In this slide here, we summarized again the Maxwell's equations, the four Maxwell equations, in the differential form on the left and in the integral form in the right. Now, this all looks pretty complex, but the reason why we did that is that we can now, in the following 5 or 10 minutes, take a little closer look at the physical origin of these equations and where and how they are related to fundamental electromagnetic behavior of matter. Let's start with the first one, the Gauss law for electric fields. As you see on the right-hand side, a single charge is characterized by a corresponding generated electric field. If you have a dipole, the field lines connect the two poles, positive and a negative charge. If we have two equal charges, they repel and the corresponding electric field will behave like the lines plotted in this experiment here. Analytically, we can describe this phenomenon simply by the fact that we have electrical charges. If we want to calculate them, we just integrate over the distribution of the charges. And the charges are the source of the electric field E in combination with the polarization. So the charges are the result of an electric field and a polarization. So those magnitudes are connected directly through Gauss' law of electric fields, which ultimately comes from the experiment. Because if you look at a charge and you now integrate around this charge, you get the total charge Q. If you do that for the dipole, we add up the two charges, then the total charge will be 0. And from larger distances, you cannot separate the two charges. Or if they are equally loaded, then we have the repelling case and the total charge adds up to 2. Now, needless to say that the integral is independent of where and which path you choose. You just have to make sure you enclose the charges and that the integral is closed, that you really close the volume over which you integrate. The second equation is Gauss' law for magnetism. And it is formulated here in its integral form, stating that if we integrate over a magnetic induction B over a certain volume, we end up with the value 0. So there's no net flux, or in other words, there are no magnetic monopoles. To illustrate that, you see on the right-hand side a dipole, and if you now integrate over a certain volume in this magnetic induction shown here by these lines, you observe that whatever goes in is exactly the same that goes out. So there's no net flux generated in this volume other than in the electrical case with the charges. And if you integrate over a volume directly around the whole dipole, you observe the same thing. All flux that goes in goes correspondingly out. And so there's no magnetic monopole generating magnetic induction B. The next Maxwell equation is Faraday's law of induction. And you all know the example of an electric motor where we have in this case a static magnetic field and a rotating electrical wire formed as a loop, and depending on the position of that loop we get a net flux which induces an electric field and a current in that current carrying loop. So if you look at the equation on the upper right, then we see that the time change of the magnetic flux depends on the time change of the product of the magnetic induction with the area of the current carrying loop and the time derivative of that. So either for generating flux we can change the magnetic induction in time, or we can change the area of the current carrying loop. So as a consequence, Faraday's law of induction can be described as the equivalence of the line integral of the electric field over a closed loop, and this is equal to the time derivative of a surface integral of the magnetic induction multiplied by the area of flux. So now we come to the last and fourth Maxwell equation, and again we will try to project this to a simple physical law. In this case it is the right-hand thumb rule we had earlier, where a current is flowing through a conductor and generates a magnetic field just around that conductor. And Ampere's circuit law says that if we now take a line integral, so we integrate once around a closed loop, and that equals a surface integral of all current flowing through this surface. So, as a summary, we learned about the 4 Maxwell equations, and what they actually stem from are simple physical experiments which result in mathematical descriptions, and these mathematical descriptions combine the charges, the motion of the charges, and the resulting electric and magnetic fields. That's actually all. To summarize, we again listed here the Maxwell equations as we learned them on the left-hand side in the integral form, on the right-hand side in the differential form. And if you add the material equations as they are stated here on the bottom of that slide, and the Lorentz force as we introduced it in the very beginning, then we can summarize this set of equations as the tool to describe matter and fields. In a simple sentence, the charges generate electric and magnetic fields, and the electric and magnetic fields tell the charges how to move. Now, one clue of the Maxwell equations is that we can use them to directly derive wave equations from them. This is shown in the outlook picture here, where an electromagnetic wave is plotted, and you can see that the electric and magnetic field are perpendicular to the direction of propagation, which is characterized by the wave vector, and that we have an oscillating electric and magnetic field in terms of time with high frequencies in the optical range of 10 to the 14, 10 to the 15 Hertz. Now, as a second step in the outlook, we could ask the question, if we have now a resulting electromagnetic wave which we can describe, and we have the matter and the charges and the fields from the material side, what happens if we combine the two? So if we let an electromagnetic wave shine onto some material. This is seen in the next video sequence, where an oscillating charge generates a spherical wave, and this spherical wave then moves towards a boundary layer between a vacuum and a material, and you immediately see the change of the wavefront in terms of its shape, its speed, and its wavelength, and you even can see the reflection and the transmission parts depending on the material properties in this example.